So in this final topic, we're going to learn how to use the exponential regression on the calculator to find an exponential model to fit to some real-world data. So in the previous two units, we have looked at linear regression and quadratic regression features on the calculator. Well, there's also an exponential regression feature that we can use if we think data are exponentially related. So to use the exponential regression feature on the calculator, just like the linear regression and quadratic regression, you would first need to put two lists of data into the spreadsheet. So we push stat1 and enter those two lists of data into like L1 and L2. Okay, and then you would push stat and right arrow over, and next to button 0 it says to choose the exponential regression. Okay, then you need to tell it what list the values of the explanatory variable are stored in, so like possibly L1, what list the values of the response variable, so this is like your typical X and Y are stored in, and then where you want the regression equation stored so we can view its graph and use it to predict some values with. So for example, if your data is in L1 and L2 and you want to store the equation in Y1, you would push, okay, so stat right arrow 0 to get into exponential regression, and then second function 1 would type in L1, comma, second function 2 would type in L2, comma, and then variables right arrow 1, 1 would type a Y1 and then hit enter. Okay. So example 7 says to use the data below to answer the following. So time after intake in hours and the amount of caffeine in the bloodstream. Okay, so initially they took in 80 milligrams of caffeine, and then that caffeine wears down throughout the system, in your system as the hours go by. So you want to use the exponential regression feature on your calculator to fit an exponential model to the given data. So exponential model, what should come to mind is f of x equals a times b to the x. Okay, where again, this was our place where it crossed the y-axis, and this was our base multiplier when we were looking at the outputs in the table. So if we want to use the regression feature, the first thing we're going to do is we're going to put this data in L1 and L2. Okay, so we're going to go to the calculator, and we're going to hit stat 1. And I have data in these lists, so I'm going to go up and highlight list 1 and hit clear and down arrow to clear out that data. I'm going to arrow over and up to L2 and do the same thing. Clear and down arrow to get rid of the data. All right, so now in L1 we're going to put our times after intake, which were 0, and then 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. And right arrow over to L2. So directly across from 0, these are ordered pairs, so it's important that the ordered pairs stay across from each other. We've got 80, and then 72.3, 63.2, 55.7, 51.8, 42.4, and 40.9. So now we've got our two lists of data. So now if we go into, so actually I'm going to look at the graph here first. So let's go into stat plot for just a minute and go into plot 1. And it's already turned on. It's set for the scatter plot with L1 and L2, which is actually where I did put my data. So I can just push zoom and 9. Okay. So it looks kind of like we have one of these graphs for exponential decay. Okay. So within here we also had a parabola that would kind of curve down, but eventually it would come back up. And we know that unless we ingest more milligrams of caffeine, that the caffeine in our system isn't suddenly going to start to rise. Okay, so again, the caffeine is kind of wearing off in our bloodstream as time goes by. So again, it makes sense to try to fit an exponential model. So to find the best fitting exponential curve, we're going to go into Stat, over to Calc. And I gave you in the notes that it was next to button 0, but if we want to scroll down, or actually if we scrolled up, we would have got there quicker. But next to button 0, it says exponential regression. So we can highlight next to it and push enter, or we could have just hit 0 from the start to pick that off. And again, we have to tell it where we put the x values, which were in L1, comma. Y values were in L2, comma. And I want to tell it to store the equation in Y1. So variables, right arrow, 1, 1. And hit enter. So here goes our y equals a times b to the x. So here it gives us what a is and what b is for the best fitting exponential curve. And again, remember r squared, we're wanting this, if we have a good explanatory variable, the value of r squared should be very close to 1, which it is in this case. Okay, so our exponential model for this one, so again, we could just use the notation x and f, or we could use caffeine. But f of x, we had, if we round it off, about 80.23 times 0.89 to the x. We could write this, oops, we can also write that this way. How about parentheses, since there's so many dots in there, to the x. So what does the value of a represent in the context of this problem? So again, remember, if we plug in 0 for x, we're going to get 80.23 times 0.89 to the 0 power, which is 1. So 80.23 times 1. So for an input of 0, the output here is in milligrams. Okay, so this gives us, in our actual data, it was 80, but for the best fitting exponential curve, it puts that initial quantity at 8.23. So this is our, we estimate, based on this equation, that the initial amount of caffeine in the system, in the bloodstream, was 80.23 grams. So what does the value of B represent in the context of this problem? So remember that value of B is our base multiplier. So that tells us that, in this case, that base multiplier was 0.89. So as hours increases, as hours increase by 1, the amount of caffeine in the bloodstream is multiplied by 0.89. Okay. Or another way to say that is that we could say that the amount of caffeine in the bloodstream is 89% of what it was. So now we're asked to rewrite the equation in part A in this form, kind of like we did with our money that was exponentially growing. Only in this case we have caffeine that's exponentially decaying. It's getting less and less as time goes by. So if we write it in this form, we would have A of t equals, our initial value here was 80.23, and our power t, so let's go back up here maybe, and we'll use that notation to begin with. How about the amount of caffeine in the system at time t. So the form that we've written, we need a constant coefficient, which we already had, and we need an exponent of t, which we already had. But to fit the form, inside the parentheses, we need 1 plus something. We don't have that. We have 0.89. So we need something that's equivalent to 0.89. And that would be 1 minus 0.11. Okay? So, or we could have 1 plus a negative 0.11 if we wanted to write it that way. Okay, so in here, if we rewrite it in this format, okay, this gives us, in the money problem, we had a positive 0.05, and we said the money was increasing 5% every year. Okay, in this case, we said as we go on the next year, or the next hour, we only have 89% of what it was, which means 11% of it went away. Okay, so what is the approximate constant percent rate of change given by this model? Okay, that rate of change, in this case, R, is negative 11%, which means that since it came out negative, we're decaying exponentially at a rate of 11% per hour. Okay? So every hour, 11% of the caffeine that was in our system decays away. Okay? We only have 89% of it left behind. All right, so F as, what does the answer to E mean in the context of the problem? I guess we already did that. I guess this piece is actually what should go down here. Okay, here they just wanted us to get that constant percent rate of change, which is R. Okay, so R was negative 11%. But in the context of the problem, okay, that meant that, again, the caffeine amount of caffeine is decaying exponentially at a rate of 11% per hour. So now we're asked to predict how much caffeine is left in the bloodstream after 14 hours. Okay, so we want to evaluate this function at 14. Okay, how much caffeine is left in the bloodstream? That was our amount A. And after 14 hours means T is 14. Okay, so we want to plug in T equal 14 and evaluate this side of our expression. Okay? So we can do this and just plug it in, or remember we stored that equation next to y1. Okay, so on the calculator, if we push y equals, okay, we'll see that that equation has been stored for us. And so we can hit variables over 1, 1 and evaluate that function when the input, so inside the parentheses, we're going to put 14 for our input value, and we hit enter. So after 14 hours, we have about 15.6 milligrams of caffeine left in the bloodstream. Oops, I forgot what I just said, 15.6. So about 15.6 milligrams. Now H says to use the intersection feature on the calculator to estimate the half-life of caffeine. In this one, we're just going to cross that problem out. Okay. All right. So again, starting with data, and again, using that exponential regression feature to get our equation. And then recognizing here when that base multiplier is less than 1. Okay, so we're multiplying by 0.89. We're getting less and less as time goes by. So we've got something that's decaying exponentially. Unlike our money problem where the base was 1.05, something bigger than 1. So as we kept multiplying by 1.05, the amount of money in the account was growing. So we said that it was growing exponentially.